Hello, my name is Nikki Alexis Jimit and my metric number is BI241102004. So today I will be presenting about the synchronization architecture. For my part, I designed and implemented the concurrency control system for our OS engine. So this is to protect our shared data. I built a first reader-writer synchronization model using three main primitives. First, mutex, so it's to safely track active reader, and RW mutex to get keep and block incoming writers during the active reads, and a dedicated. So the last thing is log mx. This mutex to ensure our system logs print cleanly without interleaving. So on to the next page is to the system execution and logs. So it is to verify our architecture. We compile and execute the program in the Ubuntu. As shown in the threads log, multiple readers threads are allowed to query the database concurrently at the value of 100. And however, when the writer thread requests entry, it is put into a sleep queue and only granted exclusively isolation to modify the value of 150 once the very last reader exists.
Hello, my name is Gil Brian Roy, BI2411027, and I will be explaining about the synchronization engine. So our synchronization module uses two mechanisms, which are the mutex locks and also semaphores. Mutex locks is to ensure that when incrementing the read underscore count value, it is done atomically by the readers, meaning that readers can only increment or decrement that value one at a time. This prevents the race condition. Other than that, writers use the sem underscore wait to gain exclusive access, and they also use sem underscore post to let go of that access. So this ensures that once every reader is done reading, then can only the writers gain exclusive access, and when the writers themselves let go of that access, other writers can also continue and gain exclusive access. So in the output slide that I've provided here, it demonstrates what I've just explained on the previous slide, where reader 1, 2, 3, 4, and 5, they enter the file at the same time basically and reading the data. And we can see here that writer 1 and 2 just only request exclusive access and have not yet entered the file. But then once all of the readers have finished reading and exited the file, only then writer 1 enters the file and starts modifying the data. And you can also see here that once writer 1 finishes modifying all the data and leaving the file, only then writer 2 modifies the data, starts entering the file and modifies the data. So we can see here that readers, they can all share the same access at the same time. Meanwhile, writers can have exclusive access, and when they finish that access, only then other writers can access the file. That's all from me. Thank you very much.
Good day everyone. My section of the project focused on thread management and synchronization. To stimulate our multi-user environment, I utilized the POSIX library to handle dynamic threading. As you can see, in the first code block, we use pthread create to spawn parallel instance of our user seamlessly. The biggest challenge in this environment is concurrency control, specifically the classic reader-writer problem. If multiple users access and modify the same file simultaneously, the data will corrupt. To solve this, I implemented semaphores to isolate access. Looking at the second block, when a writer enters a critical section, semwait acts as a strict gate, locking out all other threads until the modification is complete. Once finished, semaphore safely release the gate. Finally, to guarantee the clean termination, the system rejoins all threads using pthread join, preventing any memory leaks from occurring. Moving on to the implementation and life cycle of this thread, the execution happened in three distinct phases. First is the spawning pace. To simulate concurrent user traffic, threads are dynamically created using a loop structure. This allows us to instantly generate our active readers and writers into the system. The second phase is coordination. Once the threads are live, semaphores take over to coordinate the traffic flow. By initializing the semaphore, we ensure that writers get absolute exclusive access to the critical section while allowing readers to safely view data concurrently. The final phase is termination. A stable operating system cannot leave a background process running. Our system waits for all specific tasks to complete and then utilize the pthread join to securely shut down the threads before safely destroying the logs. These life cycles ensure a highly stable, thread-safe environment.
Assalamualaikum, a very good day. My name is Muhammad Artifan Ramli. So I'll continue with testing and result. So for testing, I designed 7 test cases covering single reader, single writer, multiple readers, multiple writers, mixed scenarios, and a stress test with 10 readers and 5 writers. All 7 tests passed with 100% success rate. The results confirm readers access the file concurrently, writer get exclusive access, no recognition or deadlocks, data integrity verified with a final value of 350, and lastly no memory leaks. So it's clean system. On the coding side, I built test from work.c from scratch using the pthread create and pthread join, as you can see in the screen, for thread management, and seminit, semwait, and sempause for synchronization. You can see that coding in the screen. So I integrated it with main.c to use the reader and writer functions, and automated all the 7 test cases. So in summary, all tests passed, the system works correctly under various conditions, no bugs were found, and then the project is ready. So that's all for me. Thank you.